Welcome to lesson 4, example number 3. And what it wants us to find or do is check the W21 by 44 beam of example 1 for shear. I had kind of mentioned that you could check it for shear, but it's probably going to be good. But let's actually go through the exercise now. And we had, let's say what we have, W21 by 44, which when we're looking at shear, we want to know the area of the cross section, which if we go back we can take a look at it, and it is 13 inches squared. 13.0 inches squared. And we know, going back to our equations, that V max equals WL over 2. WL over 2, and I hope that makes sense because you have this distributed load. And then you want to get that equivalent load by multiplying there, and I think it was 24 foot times, what did we have? I remember it was 24 foot times how many pounds? I'll go back to example number 1 real quick so I don't give you the incorrect information here. And it is 2,000 pounds per foot times 24 foot. 2,000 times 24, and remember that's going to share equally on both sides, on both reactions, since it's right in the middle. So 2,000 times 24 divided by 2 is 24,000, which is the same thing you're doing right here. It is 2,000 pounds, PLF, pounds per foot, times how many feet? We said 24, divided by 2 equals 24,000 pounds, which is the same thing as your reaction. 24 kips, 24 kips. And if you look at think about the shear moment diagram real quick, it's going to be here's your shear diagram. It's going to go up 24, and it's going to go down 24, and it's going to go up again to 0. And right in the middle would be 0. I hope that makes sense. And that's your shear diagram, and this is going to be 24,000 pounds, or 24 kips. All right, so our Vmax is going to be right at your bearings. It's going to be 24,000 pounds. So let's move on. We now have our Vmax, and we want to think about what is our equation to find the stress. And we now have our shear max, so we now need to find our stress. And actually, what you do for shear when you're looking at a W wide flange section like so, that's a terrible drawing, but you actually just look at the web, extended web is what I'll call it, section right here. You don't include the flanges, which the flanges will actually take some, but just for the type of design you want to do, you want to assume that your web all the way up to the top and bottom is the only thing that's going to work for your stress. And what you do is your actual stress, your shear stress, is going to be V over dt, which d is right there, and then t is the thickness of your web. So I said area. You could do that, but that's typically not what we do. We just say your area of your web, your extended web, let's say. So let's go ahead and figure out what our shear stress is. It's going to be 24,000 pounds. And to figure out what D and T is, let's go back to our tables, which are going to be in your steel book. And we said it's W21 by 44, and our depth And you can see up in the left-hand corner of that table, it shows you where D is. And it also shows you where T is. TW is what they call it. Let's call it the same. TW. So D is 20.66. That is inches. TW is, and its thickness of web is 0.35. Oh, let's go ahead and put depth times thickness of web, which is pretty much A is the area. That might be confusing. Don't remember that. Just remember the thickness of web times the depth. All right. So we go ahead and put these in. Plug and chug. 0.350 inches. And we come up with, let's put that into our handy calculator here, 24,000 divided by 20.66 divided by 0.350 is 3,319. Did I do my math correctly? I do believe I did. And that's going to be in PSI, which is 3.3 KSI, which sounds about right, which is extremely small. But anyways, now we go back and we say, okay, this is our actual. This is our load, I like to put it. Now we need to look for our resistance or our capacity. And we know that FV equals 0.4 since it's shear. This is kind of a shear factor, you could say. And that's 0.4 of your yield strength. And as I said in the beginning, we're always using, and theirs is going to be 36 KSI steel, which they say it's the most used, which could be debatable. Now at times everything's going to 50 KSI, but we're not going to get into that debate right now. We're just going to go ahead and say, okay, I agree, 0.4 times 36 KSI, or 36,000 PSI, sorry. Let's say 3.3 KSI. I'm used to using KSI. 0.4 times 36 is what? 14.4 KSI. So as you can see, we're way ahead. Remember, FV needs to be larger than little fv, which is true. So you could say 14.4 KSI is greater than 3.3 KSI. We're good. And this is my assumption on example 1 was correct. We don't need to check shear in this case. There are going to be few cases that you do. I go ahead and check it no matter what, just because I'm anal like that and would rather go ahead and check rather than just assume. I hate assumptions because later on you'll follow I like to use my calcs for different projects because you'll get a good set of calcs that you like to follow, and then you end up doing that, and then somebody else will take your calcs and try to follow those, and they'll end up making these assumptions that you're not writing down. So I like to go ahead and don't make as little assumptions, or if you do make assumptions, record them at your top. Just write assumptions at the beginning, and then say bending will control if you're not going to check shear. And you can say by inspection. That means, hey, because I know better. Anything by inspection means because I have experience and I know that it's not going to work. Or maybe you just did this on the side. You did this quick equation in your head and said, oh, it's not going to control, and I know that, but I don't want to write all this stuff because writing stuff takes time, especially when you're doing pretty calcs on paper. All right. And that I guess that's your answer. Is it good? Does shear check? And the answer is yes. And you could write good for shear. All right. I will see you in example 5.